Hey guys, I wanted to run through an example problem to help avoid um, any pitfalls or caveats that you might experience when you're trying to answer some of these technical questions involving pressure, or if it's involving volume or mass, um, when you have all the other variables. So right now it's asking us to calculate the pressure um, exerted by a certain amount of nitrogen gas in a flask of a set volume at a set temperature. So when you see pressure, volume, um, mass, and temperature all together, um, probably most likely you're going to be using the ideal or perfect gas equation in order to find your answer. So, so the perfect gas equation is PV equals nRT. And pressure, so it's pressure times volume equals amount of moles times R, which is the ideal gas constant, times the temperature that they give you. And the tricky thing about this is you need to make sure it's all in the right units, and you got to be able to get to those units um, in order to get the right answer. So let's do that now, and let's get this question answered. So the first thing we're going to do is we're going to rearrange the equation and make P pressure be all by itself. So P equals nRT over volume. Okay, so let's find our number of moles. So N is the number of moles, and the way you find that is you say, okay, N is equal to, just an equation that you got to memorize, I guess, is equal to little m over big M. And so little m is the mass that they give us, and big M is the molecular weight of the gas. So the molecular weight of the gas can be pulled from your periodic table, and if you like, some things are intuitive, like, okay, so if you want to know the molecular weight of CO2, you'd say, okay, carbon is 12.01 and 2 oxygens is 16, so I would say 12.01 plus 16 plus 16. Well, when you see nitrogen, um, some things we just we'll realize that that is a diatomic element, and so when you find that in nature, it's just like CO2. You have different elements combined. Nitrogen's attached to itself, so you have usually two nitrogens. So instead of just saying 14.01, you're going to say 28.02. So so you would so the equation for to getting n is 1.25 grams over 28.02 grams over moles. Okay, so you have a double um, two. So you could say, you could flip these things around. Just remember the grams will cancel out, and then the mole will be on the numerator at the end once you do the math for this guy. Okay, so that's what our N is going to be. And our R is our ideal gas constant, and that's also just given to us. Um, so R is equal to 8.3145 joules over mole times Kelvin. And see if I can times that. Sometimes you'll see it like joules times mole to the -1 times Kelvin to the -1. That when it says to the -1, it's just saying that it's in the denominator, um, or you could just put it in the denominator. So there we go for that. And then our temperature is given to us in Celsius, but we need to convert that into Kelvin. So 20 degrees Celsius, to convert Celsius to Kelvin, all you got to do is you got to add 273.15 to it to get your Kelvin. So in this case, 273.15 plus 20 is going to be 293.15 K in Kelvin. Okay, so we have everything except for our volume, and so our volume could be a little tricky. To convert, you would multiply your 250 cm cubed times 1 meter cubed. We want to put this into meters, and so we got to convert it over to meters. So you'd say 250 cm cubed times 1 meter cubed over another value cm cubed. So you'd say 250 centimeters cubed times 1 meter cubed, and we would put a cm cubed here, and we want to know what value should we put down here, because these are going to cancel, and we'll be left with meters cubed. And so this is a tricky thing for me, and I hope that it'll help you when I do this. But so we know that 100 cm is equal to 1 meter. Alright, so we know that. So we might be tempted to put this 100 cm down here. But it's not 100 cm, it's 100 cm cubed. So it's really going to be 100. When we see that cubed on the centimeters, we're going to cube the 100 as well. And we'll cube the 1 cm, we'll cube the 1 meter cubed as well. 1 times 1 times 1 is 1. And 100 times 100 times 100 is 1 million. So 1 million cm cubed is equal to 1 meter cubed. And so we will take 1 million and put it down here in the denominator. And so here is our equation to get the volume in meters. So 250 divided by 1 million is 0.00025. Okay? And then the textbooks usually want us to have it in times 10 to the something. So we'll move this decimal place over 1, 2, 3, 4. 4 places. So that gives us 2.5 times 10 to the negative 4. That is going to be our in meters cubed. Okay. Alright. So we're going to look at this equation, and we're going to go ahead and put this below here. We'll put the volume on the bottom. We'll put our N first, followed by our R, and followed by our temperature. Okay? And I'll add little things here to show that we're trying to multiply them. And we'll see how everything cancels that we need it to. So the grams are going to cancel here. So remember, this is dividing this, and then this is dividing. So if we were to flip and multiply this second area, you'll see how the moles would go on top. So the moles are going to get canceled because this is now in the numerator and it's being divided out here. Kelvin, that's in the denominator, so it's going to be canceled as well. And we're left with joules over meters cubed. And joules over meters cubed is, that's the definition of a Pascal. Something like that. I wish it wasn't red. Okay. Joule. Something like that. Okay, so we're left with the right units. So I'm going to go ahead and quickly do the math. So this is equal to, I'm using my TI-83, 1.25 times divided by 28.02 times 8.3145 times 293.15 divided by 2.5 times 10 to the negative 4. That gives me 434,938,5573. Alright, and so there is our first answer, and that's our answer for the pressure exerted. Now if you look, it says kilopascals, so there's 1,000 there's 1,000 pascals in a kilopascal. Sorry if I'm saying that wrong. So we're going to move this decimal place over 3 times. 1, 2, 3. And we're left with 434.938 K kilopascals. Okay? And this rounds to 435 kPa. Alright, so that's our answer for this this equation. So I hope that will help someone in the future, and this can be a little tricky. So thanks.